Hello, welcome to Code Design. Today we will be discussing a classical HackerRank problem for graph theory is road and libraries. Why I like this problem? Because this problem is very close to our real life problems that we can use graph and is a very good example for solving graph problems. So first time I solved this problem 5 years back using creating a graph class and then using adjacency list of graph. Like for this problem, what we need to do, you see that determine the minimum cost to provide library access to all citizens of Hackerland. So these are cities of Hackerland. How many cities we have? We have 5 cities. We have 7 cities. And they are numbered from 1 to 8. So that means, yes, they are numbered from 1 to 8. There are 7 cities, and currently there are no libraries, and the cities are not connected. So there is dotted line, right? That means there is a edge of this graph, but it's not connected. So we need to connect them to solve this problem. And their city contains a library. So the city, each of the cities needs to access to a library. So how it can access a library, either the city has a library or the connected cities, right? Where there is a edge or where there is a path, land connection, it can go and access the library. So the problem is for given number of cities, and n can be 1 to 10 to the power 5. That means 100,000 cities. It's a very high number if we compare with some leet code problems. Generally, there are 200, 300 nodes, and this is 100,000 nodes. So this is very large. So we have 100,000 cities that we need to connect. We need to create libraries and we need to connect roads so that all the cities have access to libraries. So what is the input? So input is our n, which is our number of cities. Like for this example, n is 7. And here you can see there is cost of road and cost of library. So here cost of road is 2. So to build a road or repair a road, we cost is 2, and build a library, the cost is 3. And these are the edges, right? You see what is the input given is the edges of this graph. So I can see here 1 7, 1 3, 1 2, and 2 3. So these are edges, and we have 5 6, we have 6 8. That is the input. So the edges of the graph will be getting as input, and which we are calling here m. So n is number of cities and m is number of edges. So with this information, we need to find out how many libraries we need to uh, build, how many libraries and how many roads. So um, what are the requirement for this, right? So we need to see how we can connect these cities and how many groups of cities we can make from this one. So here we can see that this is one group. We can do one group here and another group here. We cannot connect this group with this group because there is no connection with the edges. With 5, none of them is connected. 5 is only connected with 6 and 8. So we can make at best 2 groups. So yeah, like first time when I have done it with DFS, making a adjacency list of graphs. So a graph class, and then for each of the node, right? With these edges, it is very easy to actually create a adjacency list. So for one, um, um, the list would be 7 3 2, and for 5, list would be 6. 6 lists would be 5 and 8, and these are bidirectional. So then with that adjacency list, what we can do, we can run a DFS for each of the nodes. We can visit all the adjacency needs for that one, or BFS. For DFS, if we go, we will go depth wise. And if we do BFS, we will go first all visit all the connected cities, right? And then um, explore the groups of cities. How many components is called component in graph. So how many components we have in this one. But what you will do now, if you submit or even long before, if you submit to DFS, there is a chance that you will get time limit exit because 100,000 cities, right? A DFS stack would be very deep and you may get also extract trace, so runtime error. So I don't think it will accept any DFS because I tried a couple of years back and it doesn't accept. It's just some experiment I do, and then first I did a DFS. Then after some time, when I learned DFS, this disjoint set or union find, right? Then I solved it with the union find 4 years back. And there I use a set also to use all the cities to keep track all the unique cities. But yesterday I have solved it without using the set. Actually, we don't need a set. We can make it more efficient. Still disjoint set, but no use of hash set. So now you if you see that there is a cycle here 1 to 2 and 2 to 3, then 3 to 1. Um, But we don't need actually these four, right? For if 3 to 1, we don't need it. So we can delete one of them because um, for 4 edges for graph, right? If you have 4 nodes, you will need 4 - 1. That means 3 edges to connect 4 nodes. That's the graph theory, right? So three of them is good enough. Like for here, we have 3 nodes, so we need 2 edges to connect them. So n - 1. That means if we have a group of these, we need for 4 cities group, we need 3 rows, and for 3 cities node, we need 2 nodes. Okay, so and this is a very good example of disjoint set or union find, as I said, as DFS want to work here. And let's see what is our function or what are the constant, right? Constant I have already told that 10 to the power 5 would be n, 1 to 10 to the power 5. There will be number of queries. 10 queries will be um, provided for this to test. So 10 use cases. And cost of road or cost of library also 10 to the power 5. So the number would be very long. I hate that data loss issue, right? I was using integer for them, and it needs actually long because the numbers are very long. So um, uh, let's look at first example for explanation. Here we have 3 cities, 1, 2, 3, and we can connect them like this. And what is cost of library is 2 and cost of road is 1. So what we can do actually, we can build a library in city 1 at cost x equals 2. In city 1, we can build a library, and cost of road is here cheaper than cost of building a library. So we can make 2 roads here, 1 road here with the cost of 1 and 1 road here with the cost of 1. So our total is 4. You see that this is the best scenario that with the cost of 4, we can actually build one library and connect these 2 cities. So let's look at the second example. Second example, um, the cost, let's look first at the cost. In this scenario, to build a library in a city, cost is x equals 2, and to build the road between cities 1 and 2, there is cost of y equals 1. So, sorry, this is a different one in the scenario, right? So here, that was the previous one. Now, for this one, you have 6 cities and cost of library. Let's see, sample. Okay. This is cost of library is 2 and cost of road is 5. You see that making road is very expensive, whereas you can make a library cost of 2. So in that case, if we go for building roads, it will be more expensive. So you need to actually check as a um, first step for this function, what we implement, if cost of library is less than cost of road. If this is the case, you can just make one library for each cities. That's what we are doing it here. For each of the 6 cities, it is cheaper to make one library with cost of 12, with cost of 12. And if you just make 2 roads, it will be cost of 10. So it doesn't make sense. Let's now look at the input output. So what is the input here is n number of connected cities. So I'm not going to code here. It's a pretty long code. And in my last video for lead code number of provinces, I coded this disjoint set, and now I will be improving it a little bit to adjust with this problem. Not improving, I will be customizing it for adjust this problem, and then show how I solve this. So this is n is number of cities, and cost of library, building a library, cost of building a road, and list of integer, right? Is a city ages. So each as I said, so this list, actually list of integer will have only two values, two cities, right? And this list will hold all the edges that connect two cities. So, and for this problem, okay, before jumping into the code, I will do a little bit more brainstorming. So what we need to do, we need to first find number of connected groups, right? So, or number of groups. So we need to find groups. So for this case, we have actually two groups. One group is here, another group is connected cities groups, right? And then we need to find out if there are some isolated cities. So if there is some city that is not connected, right? So 9, right? If there is a city 9 which is not connected with any of them, then we need to build a library here because we cannot make a road connection from these 9 to any of the cities. So we need to find isolated groups. So if there is a isolated group, say we have isolated cities. So isolated cities, we have say 1. So what we need to do, right? For all the groups, for this group, if we connect the roads, we need to find out how many roads for this group. So there are total actually 3 groups because this one is also a group, but only one element group and not connected with anyone. So for this one, we need to first we need to make 3 roads. For this group, we need to make 2 roads. So 5 roads and no roads here. So what would be the now our overall cost? So cost of making one library in each group. So I'm saying here 3 group, right? So for 3 groups, 3 library. What is the cost of making a library? Is 3. So 3 into 3. We are making library in 3 groups. Now we need to, so how it is coming? These 3 actually. Connected groups, we have connected groups plus isolated group. We have one city, isolated cities, right? This is a group, isolated. So this isolated one. So 2 plus 1. So we need to find how many groups we have and we need to find how many isolated cities we have because each of them will make a group. For all of them, here is 3, we need to create a library. and plus how many roads. We need to find for each of the groups how many road we need to build. Like for this one, one, two, three, right? Because four nodes we need to build three roads, and for this one, two roads. So and cost of road is two. So what's the equation is 3 into 2 plus 2 into 2. So that would be our cost with this. So 9 and then 6 plus 4, 10. That would be our cost equals 19 if there is three groups. So that would be our thing. So we'll be finding number of groups, and then we will be finding number of isolated cities. We will be finding how many roads in each group we needed. And if we sum up all the roads, then we can just multiply them by cost of road. So this is what we will be doing. So let's look at the code. We'll first look at the disjoint set. So as I said, I also have a video for disjoint set. There I went through what is disjoint set, and then what are the ways you can implement it, details. So I will have this in this video as a comment, or yes, and also the number of provinces also, where I code this disjoint set class here would be a little bit more modified. So what is more here? So this is our disjoint set, right? So we'll be using a parent array. So this is basically the representative, right? In disjoint set, each of the each of the group has a representative. So like for this group, we'll find one representative node. For this group, we'll find one representative node. It's easier to view them as a tree, so that's I'm naming it as parent node. But it is basically the leader or of that group, or the representative of that group. Now we have a rank array, so we can use rank for balancing the tree path. So whatever tree path we are doing right on disjoint set. Um, so like this one, if I say one and then three, two, and four. If we think it as a tree and one is our representative, then this is the path, right? So from four, if we say find, disjoint set needs a find method. So for the find method, if we provided four, it will give us the representative of that group. So for four, the representative is links to two, and then two it points to one. So one is the representative for four. So if we say find of four, it will be one. And then if we say find of three, it will be also one. If we say find of two, it will be one, because one is the representative of this one. And this is the path, right? So we want to make this height balanced as small as possible, so that you don't have to go through all these nodes. We'll be using that rank to balance, and then size, right? We need to this is the difference. Like my earlier implementation of disjoint set don't require a size, only rank was good enough, but here we need the size because we need to know the size of each groups. So here there is a we need to do a initialization. When you call this disjoint set, we pass number of cities, we create these arrays, and then we initialize the parent array. So for each of the representative, right? Initially for this one, each of them will be the representative will be the same node. So when they are not connected, so one will be representative one, two will be representative two, four will be representative four, something like that. Initialize, right? And the size when they are single nodes, the size is one, right? At least one node in each group. As I said, isolated cities, right? Isolated cities will be a group with only. So if there is a isolated city here 10, that will be only one group that points to 10 itself, representative of 10, and size is one. That's what we are doing it. Now for the find, right? For the find, if you see, if x not equals parent of x, so this x is 4. 4 is not parent of 4, right? Parent of 4 is 2. Then 2. 2 is not parent of 2 because parent of 2 is 1. So, but for 1, parent of 1 is 1. So there it ends and find the representative. So a parent of 4 is 2. Parent of 4 is 2, and they are not equal. So again, this find recursive call will be there with 2. Now it is 2. When it is 2, parent of 2 is 1, and parent of 2 is 1. And then for 1, what we get? Parent of 1 is 1. So it will return. When it will return, what we will get until ultimately this find they will return from one another, right? For when you call it for 4, it will go to 2, and for 2, it will go to 1. And when it find we go to 1, then parent of 1 is 1. Then actually it will the recursive find call will return the data. So it will return here. First, it will return this one value will be one. Then it will return here, and then it will be return here. But here, what we have? We have here parent of x. That means parent of 4. So what we get? Parent of 4 equals 1. We get the parent of 4. And for this find, right? Of 6, if we have 6 and we have 5, and if 5 is representative of this one, then when we call 6, parent of 6 is 5, and then let's say 6 5, right? So if we call with 6 here, parent of 6 is 5, so they are not equal. Then we'll call again find with 5. When we call it 5, parent of 5 is 5. So that is then we return. So the same way, parent of 6, if we call parent of 6, it will be 5. So representative of the group that contains 6, parent of 6 equals 5. And the last one, so we have a single group for this group where I draw it. Okay, here 9, right? For 9, if we call parent of 9 is 9, so it will return. And what we'll have? We will have um, parent of 9, parent of 9 equals 9. Then we can find, if you see that we will also keep track of the size. So for each of the representative, we can get the size from the size array. And this is how it works. Okay, let's look at our union function, unite. So what we do here, I have here 3 use cases. So we'll be running through it. Say for first use case, right? So for we have two groups here, two disjoint set. One is 1, 2, 3, and another is 4, 5. For this one, 2 is pointing to 1 and 3 is pointing to 1. That means 1 is the representative of this group. And for this one, 5 is pointing to 4. So 4 is the representative of this group. So U and V, right? Here U would be 1 and V would be 4. So, um, so that is the leader, right? But say we are actually doing with this, say for 3. So 3 and 5. So U is 3 and V is 5. Say we want to unite these two group with these two elements. We have element 3 and we have element 5 from here. So when we do it from 3, right? So it will call the find function. So find of 3. Find of 3, what will do? It will find the parent of 3. Parent of 3 is 1. So it will return 1. We will get here 1. So parent I equals 1. And for J, we have 5. So parent of 5 is 4. So we'll get J equals 4. So I equals J. They are not 1 and 4. That means they are in different group. So let's see. It's a rank, right? So this one is a bigger group. So the way algorithm is implemented, bigger group when a group is bigger, we increment the rank. So bigger group has higher rank. This is a strategy. You can make any strategy. So if rank of I greater equals rank of j, so rank of 1 would be greater than 4. Then in this case, because it's a bigger group, what we do, parent of j equals I. So parent of 4, we say parent of 4 equals 1. So we'll connect actually, make this one, parent of 4 equals 1. And the size of 1, right? Size of this group which has a representative 1 would be size of I plus size of j. So size of I equals 3 plus here 2. So size would be 5. And when both rank is equal, right? If the both rank is equal for any case, like this case, rank would be equal for 9 and 10 if we want to join them, right? Rank would be 0 and 0. They are individual components. And then we um, increment the rank for either one, either 9 or 10. So we are doing it for 9. So we are increasing rank. Else, what is the condition? When rank I is less than rank J. That would be case, say, for these two, 3 and 6, 7. If we are doing it for 3 and 7, if we do it for 3 and 7, then parent of 3 is 3 and parent of 7 is 6. So 3 and 6. What you can see, rank of I actually less than rank of j because 3 is a smaller group. This is a bigger group. So what we'll do here, parent of I equals j. So what we do, parent of 3 will point to 6. So that would be the case. And size of j, right? Size of this group would be now size of them means size of 6. That means this group is bigger. So the other group size we ignore. We don't care. We don't need it for this union find. Size of 6, size of this size group is 2 and is 1, right? 2 plus 1 or 1 plus 2 is 3. So this is how union works. Now for this one, number of group count, right? So if you see, we have three groups. What are the representative? For this 9, right? Representative of or parent of 9 would be 9. So for 10, parent of 10 would be 10. For this group 2 and 3, parent of 2 would be 1, parent of 3 would be 1. So we, in this case, for all the nodes, if parent of I equals I, right? Like for one, parent of I would be 1, 1 itself. So we'll increment count. So our count is now 1. For this group, this group 4, 5, right? Parent of 4 is 4. So 2. So for this thing, we'll have a group count of 2. So this is how we find the group count and total rows, right? Size of I means number of element in that group. So if we are considering 1, 2, 3, number of element is 3 before merge. So if we have 3 cities or 3 nodes, there will be 3 minus 1, n minus 1. That means two rows. We can build two rows. So total rows will be sum up 2. And here total connected cities is 3, right? Total connected size of by 3. So this is for one. And when we do it for say this one, this thing, there will be total road will be 2 and total number would be 3, number of cities. So this is our union. And now, okay, I clear it. So this is our input. We check if cost of library is less or equal to cost of road, right? If cheaper to build the library, we just need to build library for each of the city, and that will be our result or output. We return from here. And if not, this is our cities, right? List of edges. So for each edge, we have what? City one and city two. Like this city is connected to city one is connected to seven, something like that. So we do the unite function for each of the edges of the graph, whatever edges we have. And after this one, the groups will be created. Then what we say? We say num connected groups. ds.num groups count. We pass the n and find number of groups. That means connected groups. Then total connected cities. So for each of the group, there will be cities, right? So if we have three cities and they have nine, if we have three groups and each of the group has three cities, three groups and three cities, then total cities would be nine. So total connected cities. And if I have an isolated one, say I have an isolated element 10, so total number of isolated cities would be total number of cities minus these total connected cities. So which would be 1. So now what we have to do, we have to build library for each of the connected groups. If we have three groups, we need to make one library for one group, right? For this group, one library, this group, one library. Then isolated cities, right? Say if I have another isolated city here, right? For that isolated city, we need to build a library. So this is we are done with library, and let's see path, right? So how many paths we need to for this group? We need to make three paths. Is for this group we need to make one path. 3 plus 1 4. So this is total roads we need to build and multiplied by cost of road, which will be our output or which will be our result. Time space complexity, right? So what we are doing, our unite function has a complexity of O of alpha n. This alpha is called inverse, alpha function is called inverse Ackermann function, which grows very slow. It is almost constant time for unite with path compression, right? With path compression, we have used path compression here. Time of complexity is alpha of n. And how many edges we have? M, we have 6 edges here, right? So for if edges, we are going to call this unite function. So it would be m of alpha n. So the overall time complexity is O of m dot alpha n. This is our time complexity for this program. And space complexity is On. We are using parent, rank, size, or all the arrays which are On size, which are n size. So space complexity is On. Okay, I hope you like this video. Let me know. Thank you.